Hello and welcome, dear learners. I'm very happy to welcome you here now in the seventh module of our battery course series, and today we will talk about challenges in battery industrialization. My name is Bastian Manz. I'm working for Permotion in our Mexico office. I've been working in e-mobility for 6 years now, and I'm happy to guide you now through the latest challenges in battery industrialization. Hope to widen a little bit your perspective, maybe tell you something new so that you learn something, and excited to have this chance to be your teacher here. So during this lecture, we will take a closer look on the challenges in the industrialization, and after watching this presentation, you should be able to have an understanding of what actually is the industrialization and what are related challenges to industrialization. We want to also show a little bit the special challenges in product design and development. And we want to illustrate product and process validations with the help of examples and give you a little bit more context on what can be then eventually concrete challenges in the production chain of batteries. Yeah, and without much further ado, let's dive into the topic of industrialization. And more specifically, we will start this by having a look here at the current battery cell production projects in Europe. So here you have an overview provided by batterynews.com of the latest battery cell production projects. That is roughly a year old, but it shows you the latest the latest developments, the latest projects, the latest investments. So you can see here a lot of production projects are happening in Germany, in Eastern Europe. As you can see here, in Hungary is a hub for that. France, England, also Spain had some smaller projects. So in general, there's a lot of activity in the construction sector, which leads then to battery production plants and cell production plants. Question which is critical here is how can the implementation and commissioning of these announced project plans now for battery cell production be successfully realized. As you see here, a lot of announcements have been done, a lot of announcements have been made, investments have been promised. Nevertheless, they also need to be now implemented and realized. And the magic answer for this is industrialization. So through the industrialization, we can guarantee that the implementation of production plans, for example, here in Europe, can happen smoothly, efficiently, and without delay in timelines and without any interruption. Now going a little bit deeper into what industrialization with regards now also to the battery cell production really means. And we have here a little bit of an overview. On the left side, we have the different stages of the industrialization of the different industrial revolutions, starting here with the Industry 1.0, with the development of the steam engine, then Industry 2.0, the mass production of specific products and goods, Industry 3.0, automation and robotics, now including first robotics into the production, automating more in the production, and like this achieving higher outputs and higher produced parts. And now finally we are in Industry 4.0. So cyber physical systems are implemented into the production. We are implementing more machine learning tools. We are digitalizing our productions. Usually we connect more. We try to improve the quality in the production through digital systems and machine learning, etc. So the definition for these terms could be that the societal and governmental advancement through technological process that occurs with increasing goods and services. Now looking a little bit more on the industrialization in the field of production. Here on the right side, we will have different phases also. This is usually starting with the development phase or ideation phase. Also in this phase, usually in terms of batteries or mobility products, the first sketches are done, the idea is sketched and is developed like this. So it's kind of like the planning phase a little bit. Then we enter a prototyping phase where the product design and development is going to happen, and also the process design and development. So usually here we will develop a couple of prototypes without any standardized production processes. So more to reach these prototypes to see if the functionality of the product is good, if it fulfills the purpose that we want to see in this product. But at the same time, we already start also with process design and development until we then reach basically a pilot phase. In this pilot phase, we set up our product and process validation that actually happens already a little bit before, also during the prototyping phase already. However, this pilot phase is super critical to prepare us for the serious phase, for the serious production, which will then happen at the end once our process design is completed, once our product is validated and completed, and after, of course, we evaluated feedback and corrective actions into our product. So the definition of the lecture would be that all activities in a manufacturing company to develop and produce a product in a defined quantity, in a standardized, reproducible manner, and in compliance with quality standards. So this is where industrialization wants to lead us. Now, taking a closer look on the challenges in the industrialization of a battery production, because that is still here the topic. We will dive deeper a little bit into four main chapters. So we will first have a look at the product design and development, battery cell specific. Afterwards, we will have a look at the process design and development, followed by the product and process validation, and eventually by the production startup. So let's dive now into the product design and development. So market diversity of commercially available lithium-ion batteries is huge. So you can see that here just with this short or small selection of batteries that we included here. There's a huge variety of batteries in all different types of sizes, in all different formats, different cell chemistries, etc. So the variety of battery cells available on the market is very big. Also, different designs are required depending on the application and also on the requirements, obviously. So like this, we are dealing with a huge amount of different battery cells. So how can we now kind of find a common ground for this, and how can we see how product design and development really affects in the end the industrialization part. So here you can see on this very slide that the product development process of a lithium ion battery is majorly defined by 4 main steps or 4 main categories, which is one, on the left side here, the material, then the format of the battery, so what type of battery. There are only 3 battery formats, but then the dimension is also a different category, and finally the design of the battery. And then in the end, out of this we will have various product variants. As we saw already in the slide before, there are a huge amount of different battery cells and batteries. So these are basically our 4 design gates for a lithium ion battery. And now in the following, I want to take a little bit of time and dive a little bit deeper into each of these categories so that you create a better understanding of what is important in these stages, what are factors that might be relevant now, and at the same time, please also take the opportunity after watching now that video to have a look again on these slides. These slides and these inputs are very information heavy, so it might make sense to revisit now this section after you watch the course for the first time. So starting now with the material. So basically now what we do have here now is the definition of the cell chemistry as part of the material. So the cell chemistry is a central building block for the battery and of the battery, and is always defined depending on the application. Research and development activities usually focus on optimizing these materials in terms of costs, performance, and sustainability. Sustainability, if you remember the previous lecture that I presented to you on the aspect of sustainability in battery production or in the product also, we learned that, for example, cobalt has quite some high sustainability impacts on the greenhouse gas emission side now. So that is part of these research and development activities that in the end then affect also the definition of the cell chemistry. Here in the graph, we've listed a selection of different battery cell chemistries in regards to their technological readiness level. So basically how far the cell chemistry is ready to be industrialized. Technological readiness 1 to 3 is a very early stage, so that would be like maybe in the concept in the development phase. Technological readiness level 4 to 6 would be a little bit more advanced, so there would be available some prototypes maybe that could be evaluated. And then technological readiness level 7 to 9 is literally the preparation now for the industrialization and for the series production. Also, you can see here a little bit the different selection of cell chemistries. Some with a gravimetric energy density, as well as the volumetric energy density. These are available for both or for all cell chemistries. Commonly used materials in that regard are at the moment, like for cathode materials, are for example LCO, which always has a high durability and safety. LFP is very common and very popular at the moment, which has a high life cycle stability. LMO provides high discharge current possible. The NMC optimized properties, and so on. Also, each cell chemistry provides some very specific advantages. On the anode material, there we usually mainly use graphite. Also, has been throughout the last years. However, graphite is kind of conquered a little bit by silicon. So silicon provides a very high energy density, and a good cycle behavior. So it's gaining a little bit more traction. So this is a first good overview, basically, to show you how the material during the product design and development process during battery cell production is affecting and has been done to help kind of set up the industrialization and the production. Now, moving now forward. Now let's have a look at the format, the cell format selection. So the selection of the cell format is always depending on the cell size, the capacity, as well as the structure of the subcomponents. So these variables are usually predefined to a certain extent. That depends a lot on the application. In terms of electric vehicles, that depends then on also the architecture of the vehicle. That depends on a little bit the electric drivetrain design also, and existing supplier relationships. So if an OEM, if a car manufacturer has been produced or has been used cylindrical cells for the last 2-3 years in all their platforms, it's not so likely that they would choose a prismatic cell and do the switch. So they usually would continue or develop the cylindrical cell further, expand it, make it more efficient. So that is usually the case. Special formats have been therefore developed for special occasions and special applications. And over the years, we can see that here from 2021, that's a little bit of projection also how we expect kind of the battery industry to develop. But these main three formats are dominating the market. Now here is the pouch cell, this is the cylindrical, and this is the prismatic cell. Here we see actually a small, here in 2025, a small increase or relatively big increase in the cylindrical cell adoption and production. So it's going to be interesting to see how that will continue, and also for which different formats the specific OEMs will set their models up and design their models. Technological developments and innovation can strongly influence the relative share of the different cell formats in the market. However, there's no indication of a dominant or strictly preferred format. Now, that's basically what I just said. It's not yet clear really if a specific format will take over. Yeah, that's something that we will need to see. So moving on now, we will have a look at the dimensions. So that is basically in the product development process, the specification of the cell size. So here you can see in this graph, you can see really the dimension, shortest side of the battery, and here the longest side of the battery on the x-axis. And this shows very well how over the years most of the batteries or most of the cells have been really rather here in the smaller sizes of the dimensions, whereas every now and then we have some larger batteries maybe for specific applications, but it's changing a little bit. We have here for example, here the S volt blade cell is something that has way larger dimensions, as well as the 4680 cell of Tesla. However, we didn't include that here. But throughout the last years, we have seen a big trend that the cells are growing more in size, have a higher energy density, and simplify like this also a little bit the construction of battery packs, of drivetrains, by simply using less and fewer components. Important here is that the dimensions of the cell stacks or jelly rolls, as well as of housing covers, have a very big range so far now, but again, the trend goes towards the bigger cells and just to create higher energy density. Moving forward and kind of closing off now here this product development process, we will have a look at the cell design creation. So the cell design, or the design of the cell design, is the positioning and the design of the taps that influence then the final appearance of the battery cell. So you can see that here, for example, here in this pouch cell, you can see that the taps are out there. Here in these cells, we have taps on the sides, and also this varies depending on what type of cell, what type of application we are using. So very dependent also on the integration into the final product. So depending also on the vehicle architecture, depending on the drivetrain design, these cells will be then implemented and assembled into the battery packs, and accordingly they would need to fulfill certain requirements. Also, that is basically the last part, the design part of the product development process. Interesting also is that current developments are showing a growing pouch cell size. So that has been growing here in length and thickness, with tabs on opposite sides. So that is basically this one here. The design freedom leads also to a variety of different cell configurations with different product characteristics. So that would be here then adaptations basically of the cell. So kind of now summarizing this a little bit, recent changes in the product design and development also led then to new battery cell trends. So we've touched base on this a little bit, that the change of cell dimensions is happening a lot. Simply that through different applications, through different vehicle architectures, how the batteries can be implemented into the drivetrain, into the battery pack, that also the dimensions are changing and will be changed for that. And also the trend these days is that the cells are getting bigger, and larger dimensions offer higher energy density on the cell level. So that's definitely a benefit. And parallel to this, also cost potentials can be realized. Larger cells, higher energy density means in return that we won't need as many cells per battery pack or per electric vehicle to reach the same capacity, which will be, of course, also seen in or realized in fewer production steps, simpler production steps, and more value creation through these production steps. At the same time, also trends are influenced by innovations in the cell design. So that could happen, or that happens most of the time, through new research findings. For example, a new production process, or an adjusted production step that simplifies certain things. So that will simplify also, and will also make specific cell designs more attractive. Then new battery pack designs are also requiring modified cells. So that is again the pull that is coming from the application side. Here you see, for example, cell to pack. Cell to pack is a way of cutting out basically the assembly part where battery cells are stacked into modules, and these modules are stacked then into packs. So like this, we can save time, resources, weight on the process side, time and resources on the process side, and weight on the product side of the final battery. And all of these, like basically innovation and also the change of or the varying cell dimensions, interfere then in the end and create new trends. And as you can see here down there, for example, the BYD Blade battery, it's a prismatic battery that is such an innovation, or the Tesla 4680 cells, that is a cylindrical cell, but Tesla significantly increased the size and the dimensions, or the Volkswagen map format, which is based on a pouch cell. So, finishing off now the product design and development step on the battery cell specification side, we are moving now to the process design development step for the design of production technologies. As already presented during the last presentations and our last lectures, we always have to look on the one side on the product side, but on the other side also on the production side, how are the batteries being produced, or what are steps that can be made smaller, shorter, where can we save money, where can we increase our output, maybe through new technology. This is all on the production side, and obviously that's a key factor in when looking at the industrialization of a battery production. So moving now forward, it's critical to understand central product and process futures and also how they interfere with the production process. Also, basically, I mentioned that recently, that also the cell design and the dimensions and all the characteristics of cells is very much influenced by the application, and also by the final purpose and requirements for the batteries. So at the same time then, it doesn't come as a surprise that the production process of so many variants and so many different designs of batteries is also highly influenced and interacts a lot really with the specific cell design and also the battery purpose. So that's why you can see here on the top basically these factors like material, the design, the format, and also the dimension that then in the end affect basically certain or interact basically with certain production steps. Literally from the very beginning, from the electrode production, speaking about anode production and cathode production, then to the cell assembly, cell finalization, all the way until the end, until we have pouch cells, cylindrical cells, and prismatic cells, as shown here. So yeah, this is extremely important to understand really the interdependencies that we have between the specific product design and in the end the production process. So that is something that every battery manufacturer need to understand, how or which product feature is influenced by which process and in what way, and vice versa. And one way to kind of help really to understand what production technology or what line configuration, what line setup helps and is kind of the solution. I would like to present you now here the morphological box approach, which is kind of a tool that helps to really understand now the different criteria of that need to be considered when selecting equipment or machine, and finally also to configure the line. So it is here in basically 6 different steps. So we start with the initiation. In the initiation at step 1, where we list all battery relevant technology alternatives. Also, if we would be looking, for example, at a certain production step, like the mixing step, here we would list basically all alternatives. In step 2, we would list and define the evaluation criteria and the rating scale. So understanding really, okay, what needs to be fulfilled to produce our or to do the mixing, and to be conform with our battery product or our cell. Then in the 3rd step would be then the methodology. So here we would do the construction of the box with all the technology alternatives, and that would be then basically the main part here of this funnel, the morphological box approach. In step 4, in the evaluation, we would evaluate the individual technology alternatives and kind of derive an evaluation count or score, which in the end will help us then to make a ranking of the best suitable machines or alternatives or equipment, whatever it may be. In 5, the selection, we would select the highest rated technology, and then in the destination phase we would do the line configuration. Also, that would be then kind of the implementation. Yeah, here's basically a little bit of input now. So that is how a technology evaluation could look like, making a little bit of one-pagers that show the different characteristics and stats from each technological alternative, and that could be then evaluated in the end. Yeah, then in this step, we are looking to increase basically the product and process quality, as well as to reduce the process time. So that is focusing on also basically a mapping and an understanding of how the different technologies, machines, or different equipments that we have in our production chain add up to the overall production time, and more specifically to the specific production time of each step, in order to find the best setup that creates for us, aligned with our requirements, with our target product, then the optimal setup and the optimal process quality as well. So here in this, it's basically here a graphic that we're working with. So we have here the process performance on the left side. This is measured in parts per minute or seconds per cell that you can see here. So for each battery cell, it will take a certain amount of seconds. And on the lower side, process quality, whereas this now doesn't have a specific measurement scale, but there are also the various parameters for process quality. However, that's more now an example. So during when setting up our production, we want to target, and also after it's running, we want to target a specific corridor that has, on the one side, the desired process performance, so producing a certain amount of parts per minute, and at the same time has a specific process quality. For the optimal design of this process, now the interactions also between product and process need to be considered, obviously. So here for the product optimization, there's some things that we can keep in mind, especially when looking at battery production. So for example, that would be here: no foreign particle inclusions between individual layers of electrode and separator. That goes a lot into technical cleanliness of the battery. Damage-free handling of electrode and separator layers. No cross-contamination between electrodes. And for the process optimization, we would look at a high positioning accuracy of with less than 150 micrometer, and a minimal process time with under 0.4 seconds per sheep. And this I should have mentioned that at the beginning. This here is the example of the step of stacking. Now, moving forward, when setting up a production, it's yeah, particularly important to have a robust integration of all processes into a holistic production concept. However, currently still that presents a challenge, simply due to the reason that there's no equipment or machine manufacturer working in the battery space at the moment that is producing or that is offering a battery production chain that covers really all the different sections of the battery production, of the cell production. So we will always have to, or at the moment, still have to work with multiple suppliers in this field, multiple suppliers that are providing the different machines, and that in the end will then combine to our full production. That, I mean, here on the left side, you can see this, that's an example now. So here are some supplier of different equipment. You can see here the different process steps and what they would provide now. In the end, it's very complex setup like this now, and yeah, again, it's really dependent on the application. It's dependent on the specific machinery. So it's really, it's gonna take really some time to do and to create that understanding of what is really the best setup for your battery specific, or for your battery production. It has to always be balanced a little bit, or chances and risks always have to be balanced individually for each process step. So on the one side, the chance is the selection of the best possible process technology. So ideally, technology leader, market leader. At the same time, this is combined, of course, with risk, because high efforts for linking and coordinating different systems will happen in any case. And if you, of course, also choose the technology leader in the same time, you would also probably have to expect to pay a higher price for this investment or for this machinery. So yeah, this is very complex. This is something where companies, where battery OEMs spend a lot of time on during the planning and the setup and the construction of their battery plants. But it's definitely an opportunity also to make the industrialization of the cells and the production better, and have, in the end, if you do it right, a more productive battery production. Yeah, that was the production side of the process design and development section. We will now have a look at the product and process validation, and we'll check a little bit on technology continuity and scaling. And basically for this, I would like to start with product, process, and interactions become apparent. Now, that's basically just a short example for the coating product futures versus the process challenges in wrapping. So in the coating, you can see on the left side, in the coating, the product process interactions affect the possible production capacities. That's the example of a round cell. And intermediate coating is necessary to leave, or in intermittent coating, it's necessary to leave a gap for welding on the current conductors during the wrapping. So this product feature affects really here the process of the wrapping and presents a challenge. So the high product and process requirements demand a defined machine specification to stay then the tolerances, and basically the inaccuracies in the production of the jelly roll, what happens during the wrapping, can lead then to defects in the later process. Now, however, these inaccuracies we will have to a certain point through this gap, and that will be then found, or will be implemented / we will find then these interactions of this product future again in the process step of the wrapping. The next example is basically the proof of performance in wrapping. So that's going more towards the definition of quality acceptance criteria during the whole process. So here the verification of all machine specification in different scenarios has to happen. The proof also includes ensuring that the product requirements and process characteristic with over 100 characteristics is achieved. Commissioning of complex systems can take several weeks to months until the established process is also achieved. Also, that's kind of a additional setup time. And many quality features of the battery cell can only be validated by characterization and cyclization of the final battery cell. So that shows a little bit the how basically the quality can be approved, and at what point it can be approved. It cannot be approved right away after the wrapping, but only after the final product is finished. So that's then also the challenge, that in contrast to the classical mechanical engineering, specific quality and acceptance criteria must be defined in order to ensure successful performance verification of the process system. That should not scare you, or it should just give you a small overview how really complex quality and acceptance in regards to specific production steps and processes in the battery production can be. Another section of product and process validation is scalability and technology continuity as a kind of a key success factor. So here we have this with an example of a mixer. So on the left side here, just a laboratory mixer with a capacity of 1 liter, then a pilot plant set up basically with 10 liters of mixing, series production with 75 and 400 liters, whereas then in gigafactories with gigawatt hours produced per year in these type of capacities, we would need really like an industrial mixer that has capacities around 1,500 liters. Interesting here is that like the technology continuity from prototype to series system is really required to do the successful process scaling. So the mixer that we use here for the 1 liter needs to be really needs to have the same function and the same parameters as now the mixers that we use now here for the series production. So, in that setup, with our specific battery cell, with the specific characteristics, we have to go then from the same type of mixer, but just in larger amounts and scale it up like this. But the parameters have to be the same. So that's highly important to make sure we're going to be on the safe side and also significantly reduce startup and ramp up risks during the later phases. Yeah, and that was the product and process validation. Now, last part of this lecture will be the production startup. So seeing how we would then start really a serious production and how we can standardize to continue producing at a certain scale. Yeah, and for this, I like to show you a little bit here this graph. It says mastering the production ramp up through standardization, and it shows a little bit the importance of standardization in regards to kind of to the establishment of a stable production. This graph is very easy. It shows production output in number per pieces on the y-axis, and on the x-axis is the time in the different stages that we already showed that I showed already in the beginning of this lecture. So starting from a prototyping, having a pre-series, a zero series, sometimes they call it like this. And then here really starting the run up, so where we then would increase significantly our production and have then at the end a series production, which would be then starting here from here to the right. And the blue curve is basically here this flat startup curve, and a low OEE. OEE is the overall equipment efficiency. So that is the efficiency of our production equipment, and it's usually 80-90%. So it's a range of how efficient we are producing, having basically, so you can see here, that is the curve without standardization in the production. And here in this greener color, we have a standardization in production. So what is kind of the key message here is that as soon as we have a standardization, or as soon as we start implementing a standardization in the production, we will stabilize and increase our output now. And much more in comparison to the flat start curve. So here you can see there are some deviations, sometimes more, sometimes a little bit less, but we don't have a steady growth. Still have here to fight with the low OEE, low equipment effectiveness, efficiency. But as soon as we start the standardization in our production, we will create continuity. And the crest line here, that's kind of our peak, our target production that we want to have. We will reach this with the standardization much, much faster. And in the end, be able to produce much more and much sooner. Now, this is now going a little bit into production planning and also into the strategic planning of such productions. I don't want to dive too much into this, but I think it's nice to give you a little bit of an overview. So we have basically here our ramp up. That's how it's called when you start a production and ramp it up to have serious production. We have here kind of our ramp up organization. That includes also here supplier management, knowledge and data management to start kind of prepare our series production. Also here the different stages: pre-series release, start of production, series production now. And so we would start kind of here with the ramp up planning. Here we would do the ramp up troubleshooting, now where that happens or might be necessary during the ramp up organization. And then, of course, at the beginning, we do make also prediction for our ramp up strategy, to kind of target or create targets where we want to, when we want to start producing, how fast we want to start producing, how many parts we want to start producing and everything. So that is the plan. And the more we go into the ramp up and execute the ramp up, the more this, of course, gets adjusted until we are then really in the serious production. This all along is then accompanied by technological readiness control and also change management, obviously, in case we need to adjust something, in case something of the ramp up strategy is not working, in case we have delay with suppliers, for example. So that is then something that we will need to adjust. Some methods can help here to do troubleshooting, some diagrams, some supply chain escalations, systematic problem-solving approaches. So there's some methods that could help then to speed this up. At the same time, it's good to maybe get an overview that you guys and you learners create now yourself an overview, but at the same time, maybe not super important yet. That also shows you a little bit the error source correction during the ramp up, or basically from ramp up before the series production. You see here kind of some characteristics also, and some process parameters that could be the source, or that could help you also to kind of do these corrections. In the end, the key message that I like here a lot is to have a look here at this graph and seeing here the different variables that might affect your production, or basically your series production. And here on the y-axis, the impact that it really has now. So there are some variables that have a huge effect. There are some that only have a smaller effect, and some variables have very low effect now. What is super important and very decisive during the ramp up is that you need to prioritize. You will need to prioritize what are the errors that you can eliminate easily and that have the biggest impact on your production, on your errors, or of your error sources. So that will be decisive to understand what are the impacts of the certain variables, make a ranking out of this, and then tackle the biggest impacts that you create, or the biggest error sources with the biggest impacts, and like this significantly influence and improve your production. And before we close now this section, I would like to kind of set a little bit of focus on the standardization of the production environment, here with the example during the mixing. High product sensitivity also requires high demand in the process. That is specifically here the case. However, we've mentioned that already, or we talked about this already during this lecture. Standardization increases our output, increases the production stability. So through standardization, we will also help in each single production step. So the introduction here of reference processes is crucial. The avoidance of contamination, like almost everywhere in the battery production, contamination is a huge problem for battery production, for cell production. Supplier management to ensure the quality of incoming materials, that will be a huge factor also. And continuous monitoring of product and process quality with regard to defined criteria. I guess that is self-explanatory, but all of these factors add basically to the standardization of a specific production step, in this case here the production environment during the mixing. It's critical to have this sorted out as soon as possible, or sooner than later better, and to also work on this to maintain this. Supplier management needs continuous work, continuous monitoring, that has it already in its description. And it's extremely critical to set up these standards in order to have a successful series production. And like this, we have reached the end. We talked about challenges in the industrialization of, or in the battery industrialization. So I hope you understood a little bit and learned a little bit about the concept of industrialization and its challenges. So yeah, what is industrialization, how it developed, what are challenges, and common things to consider always. We highlighted special challenges in the product design and also in the development. And ultimately, we brought some examples of the product and process validation to you closer in order to get some specific insights, specific examples, a little bit more tangible, that could help you to get a better understanding. Thank you so much for your attention. It was a pleasure for me to provide you these inputs for Module 6 and now with this one, Module 7. I'm happy to be part of this project. I wish you all the best for your continuous engagement, continuous journeys, continuous careers in the battery space, in the electric vehicle space, in Rwanda, in Africa, wherever you might see this video. My name is Bastian Manz from PEMMotion. I look forward to stay in touch with you, reach out to me via LinkedIn, and I wish you all the best and hope that you will be fine. Ciao.